In section 5.3, we look at double angle formulas. Now, I have all the double angle formulas here on the screen, and I'm going to prove all of them in just a minute. But this says that the sine of 2 times an angle A is 2 times the sine of A times the cosine of A. The next one says cosine of 2 times an angle A is cosine squared of the angle A minus sine squared of the angle A, etc. So what you should see is that the double angle, right, which is 2 times some angle A, is expressed in terms of just the angle A by itself. We'll see some examples in just a few minutes, but let's prove each one of these. So let's start by proving the first one. So we know that the sine of A plus B is equal to the sine of A cosine of B plus the sine of B cosine of A. So the way we prove the first formula is just to realize that the sine of 2A is the same as the sine of A plus A, right? Because A plus A is 2A. And now all I'm doing is I'm basically replacing angle B with angle A again. And so that just means in this formula, everywhere you see an angle B, you are going to replace it with an angle A. So the sine of A plus A is sine of A cosine of A plus sine of A cosine of A. And then you notice that these two terms are like terms, and we have one of each. And when you add 1 plus 1, you get 2 of those. And so you can see we have sine of 2A is equal to 2 times the sine of A times the cosine of A. And so this proves the first one. To prove the next formula, I will use the addition formula for cosine. And we basically do it the same way. So if I want the cosine of 2 times A, first we just write that as cosine of A plus A. And now in the addition formula, we are simply replacing the angle B with the angle A. And if we do that everywhere we have an angle B, we end up getting the cosine of A times the cosine of A minus the sine of A times the sine of A. So again, all I'm doing here is putting the angle A in for B here, which becomes this, and the angle A in for B here, which becomes this. And now we can rewrite this as cosine squared of A minus sine squared of A. And so notice that this is the first formula here. To prove the next formula, all we need to do is to apply the Pythagorean identity. And what we're going to do is replace sine squared of A in this expression with 1 minus cosine squared of A. So if we do that, what we have here is cosine squared of A minus, and then sine squared of A can be replaced with 1 minus cosine squared of A. And if we distribute the negative here, we end up getting cosine squared of A minus 1 plus cosine squared of A. And now combining like terms, cosine squared of A plus cosine squared of A is 2 cosine squared of A minus 1. And this proves the next formula. And finally, to prove the last formula here, I'm just going to go back up to this expression. But now, instead of replacing sine squared with 1 minus cosine squared, I'm going to replace cosine squared with 1 minus sine squared. And so that cosine squared of A there gets replaced with 1 minus sine squared of A. And then we still have minus sine squared of A here. And if you combine like terms here, you have 1 minus sine squared of A minus sine squared of A is 2 sine squared of A. So we end up getting 1 minus 2 sine squared of A, and that proves this one. So the thing to remember is that these three identities are all the same. They are just written in three different ways, but all those are equivalent to each other. And finally, to prove the last double angle formula, I'm going to once again make the realization that tangent of 2a is tangent of a plus a. And once again, we are going to replace the angle b with angle a. And if we do that throughout the formula for the tangent of a plus b, we end up getting tangent of a plus tangent of a over 1 minus tangent of a times tangent of a. So again, we're just putting a in for b here, which leads to this one, and we're putting a in for b here, which leads to this. And now if we just combine like terms, tangent of a plus tangent of a is 2 times tangent of a. And in the denominator, we have tangent of a times tangent of a, which is tangent squared of a. And this proves the last formula. So now that we have proven all of these double angle formulas, let's do some examples. In the first example, they ask us to find sine of 2a if we know that sine of a is 3/5 and angle A terminates in the second quadrant. So to find the sine of 2a, the first thing I want to do is put down the formula for the sine of 2a. Because this tells us that if we're going to find the sine of 2a, we need to know what the sine of a is and also what the cosine of a is. Now, they tell us that the sine of a is 3/5, right? Because that's given to us right here. But we don't know what the cosine of a is, so we need to figure that out. But we do have some information about angle A. They tell us angle A terminates in the second quadrant. So the quickest, easiest way to figure out the cosine of angle A is just to draw a picture of what angle A might look like in the second quadrant. And I have a reference triangle, and we know that sine is 3/5, and so for this angle here, sine is opposite over hypotenuse. So this will be 3/5. And then we can find the missing side here by using the Pythagorean theorem, or of course, you could recognize that this is definitely a 3, 4, 5 triangle. And so the missing side here is 4, but it has to be negative because since we're in the second quadrant, the x-coordinate of the point here has to be negative. So now from this, we can see that cosine of angle A is negative 4/5. And I'm just using SOHCAHTOA there, right? And so now that we know that cosine is negative 4/5, we can say that the sine of 2 times angle A is 2 times the sine of A, which was 3/5, multiplied by the cosine of A, which is negative 4/5. Keep in mind that 2 is the same as 2 over 1, and now we can multiply these fractions straight across. 2 times 3 times negative 4 is negative 24, and 1 times 5 is 25. So the sine of 2 times angle A is negative 24 over 25. In the next problem, we want to prove that sine of theta plus cosine of theta, quantity squared, equals 1 plus sine of 2 theta. Now, you could start on either side, but it's a little bit easier to start on the left-hand side. Now, the reason for this is because on the left-hand side, you have something that you can do here. Sine of theta plus cosine of theta, quantity squared, means sine of theta plus cosine of theta multiplied by sine of theta plus cosine of theta. And so from here, we can FOIL this. We can multiply it out, which is going to give us sine squared of theta plus sine of theta times cosine of theta plus cosine of theta times sine of theta plus, and then cosine times cosine is cosine squared of theta. All right, now let's see what we can do. Well, one easy thing to do is sine squared of theta plus cosine squared of theta. Those two together are equal to 1. And then here we have sine of theta, cosine of theta, and here we have cosine of theta, sine of theta. Please understand that these are the same, because when you're multiplying two things together, it doesn't matter what order you multiply these in. So if you want me to show the step here, I would write sine of theta, cosine of theta for the first one, plus, and then cosine times sine can be rewritten as sine of theta, cosine of theta. And this should allow you to see that you have one of them here and one of them here, which means you have two of those things. So we end up with 1 plus 2 sine theta cosine theta. Now, if you look at the left-hand side, that's not quite what we have here. But then we realize that 2 sine theta cosine theta is the double angle formula for the sine of 2 times theta, right? So we can directly substitute sine of 2 theta in place of 2 sine theta cosine theta, according to the formula. And now we have proven that the left side is equal to the right side. For the next example, they ask us to find the cosine of 2 times angle A, and they give us sine of A is 1 over radical 5. And you'll notice that in this problem, they don't give us any additional information about the angle A. They don't tell us what quadrant it's in, etc. But they also don't need to, because if you look at the three formulas that you have for cosine of 2A, notice that the last formula only depends on sine of A. So in that last formula, we know that cosine of 2A is 1 minus 2 times sine squared of A means sine of A quantity squared. And we know that the sine of A is 1 over radical 5. So if we substitute in that value, we get 1 minus 2 times 1 over radical 5 quantity squared. And this is 1 minus 2 times 1 squared over radical 5 squared, right? So when you have a fraction squared, you need to square the top and square the bottom. And this becomes 1 minus 2 times, now you have to do the squaring. So 1 squared is 1, of course. And radical 5 squared is just 5. And so this is 1 minus 2 times 1/5 is 2 over 1 times 1 over 5. That is 2/5. And 1 minus 2/5 is 3/5. In the next problem, we want to prove that the sine of 2x is equal to 2 times cotangent of x divided by 1 plus cotangent of x squared. There's actually a couple of different ways that you could prove this one. What I'm going to do is start by recognizing that 1 plus cotangent squared is an identity itself. And it might be one that you don't remember because we haven't done it for a little while. Let me bring it in here. So if you remember your Pythagorean identities, there were 3 of them. And the last one says 1 plus cotangent squared is equal to cosecant squared. So to do this problem, I'm going to start on the right side, and I'll start by rewriting this as 2 cotangent of x divided by, and then 1 plus cotangent squared of x will be the same as cosecant squared of x. Now from here, I can use basic identities. So 2 cotangent of x is the same as 2 times the cosine of x divided by the sine of x. And cosecant squared of x is 1 over sine squared of x. So I'm using the ratio identity for cotangent and the reciprocal identity for cosecant. But then we know that when we have a fraction divided by a fraction, this is going to be the top fraction multiplied by the reciprocal of the bottom fraction. So I'm taking this fraction here, reciprocating it, and then multiplying by that reciprocal. Now what's nice about this is now we can cancel this sine of x will cancel out one of those sines of x. And this gives us 2 times the cosine of x times the sine of x. Now that's the same as 2 times the sine of x times the cosine of x. And you should recognize at this point that this is the double angle formula for sine. And so this is the sine of 2x. And if you go back up to the top, that is what we were trying to prove. In this next example, we want to prove that the cosine of 4x is equal to 8 times cosine to the 4th power of x minus 8 times cosine squared of x plus 1. And I'll just warn you, this problem is pretty long. We start by reminding ourselves of the double angle formula for cosine. Now, how do I know to think about the double angle formula? Well, if you look at the left-hand side, we have the cosine of 4x, and on the right-hand side, we just have the cosine of x. So if we're going to reduce the angle 4x down to the angle x, we have to take a formula that does that reduction for us. So the cosine of 2a is equal to 2 cosine squared of a minus 1. This reduces a double angle down to a single angle, if you will. But we don't have 2x, we have 4x. So how do we approach this? Well, we're going to start by saying the cosine of 4x is the same as the cosine of 2 times 2x. So what I'm doing is I'm expressing this as the double angle of something. So in my formula, I have my double angle here, and I have the of something in the spot where you see the a. So according to this formula, we should get 2 times cosine squared of this thing, which of course is 2x. So we get 2 cosine squared of 2x minus 1. So the important thing to remember here, if you're getting a little bit confused, is that when you use the double angle formula, it doesn't matter what you have here, but what you have over here has to be half of what you started with, right? Or you could look at it the other way. This thing has to be double this thing. All right, so now if we continue, I'm going to write this a little bit differently. We have 2 cosine squared of 2x. I'm going to express this as 2 times the quantity cosine of 2x squared. Now, I didn't do anything mathematical there. I just rewrote it a different way. Now from here, I can apply the double angle formula once again to the cosine of 2x. So what is cosine of 2x going to be? Well, that's pretty straightforward. That's just going to be replacing the a here with an x. So cosine of 2x is 2 cosine squared of x minus 1. So I'm going to put that in here. And when you put that double angle formula in here, this is what you end up with. Now notice that we don't have any 4x's, we don't have any 2x's, all we have left over are x's, and that's what we wanted, right? We did not want to have any 2x's or 4x's over there on the right-hand side. So now all we need to do is multiply this out. And so just remember that when you square something, it means you multiply that thing by itself. And then we are going to FOIL here. And the important thing to remember when you FOIL is that when you multiply cosine squared times cosine squared, you get cosine to the 4th power. We have to add those exponents together. And also 2 times 2 is a coefficient of 4 here. Next, we're going to take the 2 in front and distribute it to all of these terms. And actually, you can combine these first if you want, and then distribute, or you can go ahead and distribute. Either way is fine. So I went ahead and combined these, right? Negative 2 cosine squared and negative 2 cosine squared is negative 4 cosine squared. Now I will distribute the 2 here. And that gives us the following. And the last thing I need to do is just subtract 2 minus 1 at the end, which of course is just 1. And this should be what we were trying to prove. And so let's go back up to the top. There it is. And that is what we got here at the bottom. I could barely get both of those on the screen at the same time, but you can see that we were successful in proving that. In our next example, we have another proof that we want to do. We would like to prove that tangent of theta is equal to 1 minus cosine of 2 theta divided by sine of 2 theta. And this one's pretty straightforward. You know that sine of 2 theta has a double angle formula that we can use here. The real choice comes down to the numerator. You have cosine of 2 theta, and you could use any one of these formulas for that. So how do I know which one to use? Well, if you think about what tangent of theta is equal to, you know tangent of theta is sine of theta over cosine of theta. So that means what I really want to see in the numerator somehow is I want to see a sine of theta up there. So because of that, I'm going to choose to use the third formula for the cosine of 2 theta here, right? So I'm going to plug that in because that's going to give us a sine of theta in the numerator, and I am hopeful that that is going to help us. So let's go ahead and go through that proof. So we're going to start by taking 1 minus cosine of 2 theta divided by sine of 2 theta. And I'm going to replace cosine of 2 theta with this formula. And so that gives us 1 minus cosine of 2 theta is 1 minus 2 sine squared of theta divided by sine of 2 theta. All right, so this one here is just this formula, but with a theta. So that gives us 2 times the sine of theta cosine of theta. And now let's see what happens after that. Well, the next step is to distribute the negative. So that is going to give us 1 minus 1 plus 2 sine squared of theta. And the denominator stays the same. And now the important thing is the 1 minus 1 cancels out. And we end up with 2 sine squared of theta over 2 sine of theta cosine of theta. And now we can cancel the 2 because 2 divided by 2 is 1. And we can also cancel this sign in the bottom. We'll cancel one of the signs on top. And so what we are left with there is sine of theta over cosine of theta. And there we have it. That is equal to tangent of theta. So we have proven that this expression is equivalent to tangent of theta. And that's what we wanted to prove. And in our last example, we are once again asked to graph the function y equals 4 times cosine squared of x over 4 minus 4 times sine squared of x over 4. And what I'm going to do to help us start is I'm just going to factor out the 4 that you see in front. So we have y equals 4 times the quantity cosine squared of x over 4 minus sine squared of x over 4. Now, you know that you can't graph this, right? This is too complicated. We've never graphed anything like this so far. So you know that there must be a way to simplify this expression. And we can by using the appropriate formula. And that formula is the one you see here. Notice that cosine of 2a is cosine squared of a minus sine squared of a. And that's what we have right here, right? Cosine squared of x over 4 minus sine squared of x over 4. So what we have here is this formula, but for a, we have x over 4. So what is that equal to? Well, the formula says that it's equal to cosine of 2 times a. So if a is x over 4, this is going to be the cosine of 2 times x over 4, which is x over 2, right? Because we can cancel 2 goes into 4 2 times. So that means I can replace this with the cosine of x over 2. And so we are graphing 4 times the cosine of x over 2. And now this becomes a simple graphing problem that we've done before. We know the amplitude is 4, and we know the period here is 2 pi divided by the number in front of x. Now the number in front of x is 1/2. So 2 pi divided by 1/2 is 4 pi. And so what we're graphing here is a cosine graph. Amplitude is 4, period is 4 pi. And so cosine starts at the top. The period is 4 pi, so it's going to end at the same place it started. Halfway in between at 2 pi, it will be at its minimum value, which will be down at -4. And then halfway in between those two values, it's going to cross the x-axis. And so that graph looks something like this, right? And that's not a very good graph. I'm not doing a good job. Let me clean that up a little bit. That's a little better. Okay, so that's what one cycle of the graph looks like. And then, of course, we could extend that in the other direction by putting in our important points here and here, here, and here. And then we can extend the graph this way. All right, so the important thing here is to recognize that this is a complicated function. We don't know how to graph something when it's written in that form. So we look for a formula to help us rewrite it into something simpler. And then we can use previous knowledge to help us graph that.